So just bear with me, please.
So, hello everyone and welcome to this webinar. I hope you can all see my screen. Adam, can you see the screen fine? Adam?
Yes, we can see, yeah.
Okay. All right, so we'll show you today how you can do some calculations with respect to power handling of various microwave devices. What I'm showing today is a specific structure, but this feature will work for obviously any arbitrary situation where you have a mix of metals and materials and so on that you want to look at power handling considerations. So before I get started, I want to just maybe make it clear that so for power handling, there are two key issues that microwave engineers need to worry about. One issue is, will there be a dielectric breakdown? In other words, will the electric field reach a certain level or a certain voltage such that you'll have arcing in your structure? And this kind of breakdown and or limitation on power handling is usually what we associate with what we call peak power handling. So if you buy a device, usually you're going to find a peak power rating and an average power rating. So the peak power rating is what we're talking about when we're talking about dielectric breakdown. Peak power typically will occur in a system for very short periods of time. So it's really the strength of the dielectrics and the insulators that you have that will be limiting that factor. Okay, and we will cover this in this webinar. We'll show you what we mean by that and how you can get these numbers through HFWorks. The second aspect of power handling limitations is the thermal aspect. So if you have quite a bit of power, but not peak, but it's continuous power or average power that you're operating at, then the problem becomes one of not necessarily breakdown, because you can't be at breakdown. You're going to be less than breakdown, but the structure can heat up. And then if it heats up and if it exceeds certain limitations, certain temperature limitations, then you can consider that device will not work, will not handle that level of power. And that also would be another feature that we would show you. All right. But before we get started, I want to just give you, for the benefit of those who have not seen this before, so SolidWorks is the #1 CAD in the world, and this is for laptops and PC-based computation platforms. You build your model. In this case, we have considering a coax to a double-ridged waveguide transition. And we want to see this structure, okay, how much power it's going to handle. But to start off, we want to see if this structure, how far does this pin, this is the central pin of my coax, I'm going from coax to waveguide, so how far does the central pin have to go? And how far off the back wall, okay, if I make this thing transparent, then we can see that the distance from this pin to the back wall and the depth are two parameters that will determine, okay, how well or how matched the device is. So this is something that you need to get figured out before you actually start thinking about whether it's going to be, you know, how much power it's going to handle and so on. So the way we do this is actually we've set up through SolidWorks. SolidWorks offers something called multi-configuration. We have 3 different positions. So if I do this this configuration, you can see that if I move it a little bit and penetrate a little bit, this is what I call position 2, then position 3, and then I have a default position. Now HFWorks, as you can see, is fully embedded inside SolidWorks. So it's really not a separate piece of software. It's essentially part of SolidWorks. Okay. And the way HFWorks does the simulations is essentially we read the model from SolidWorks, in this case the coax to double rigid waveguide transition, which is the solid model, and then we create studies. So in this configuration, now I'm looking at configuration 2, which is position 2. I could also look at configuration 1, which is, this is a first configuration. And I've actually went ahead and did simulations, okay, for the 3 configurations, and I can show you what the simulation looks like. So essentially you have the different materials where we assign a material property to each body. So we have the air part here, and we have the coax, which has a dielectric part, which is Teflon, and it has an outer ring, the conductor part, and then we have the double rigid waveguide itself. So that is, these are my 3 parts in the assembly for which we've defined materials. The next step is to set up boundary conditions. So in this case, the key boundary conditions that I had to set is I have a first port, which is, this is my entry port where the energy is going to come in, and this is my exit port, or this second port. The energy could also come in port 2 and come out of port 1. It's a fully symmetrical structure. So so the boundary conditions allow us, obviously, to set up. Notice we have a folder here called implicit boundary conditions. So all internal surfaces that are touching the metallic parts, okay, get automatic boundary conditions. So we know that the air is touching copper, and so we know I have a copper boundary condition automatically defined. Okay. So after we do materials and boundary conditions, we usually generate a mesh. It's an automated process, and I can show you what this mesh looks like for this model. Okay, so we have the mesh automatically adjusts itself to feature size and so on. So this is a very nice and feature in HFWorks. We also have the ability to control the mesh locally through what we call the mesh controls. So in this case, we set in the coax section, we wanted to have a sufficiently small element size, so we defined that through a mesh control. So the 3 steps are that set up the studies are essentially, like I said, the material definition, the boundary conditions, and the meshing. Okay. Now, once these are done, we run the problem and we obtain a result. So in this case, if I want to look at the results, I can look at these in many different ways, obviously. I can look at the results table. I can generate plots and so on and so forth. I can look at field data and so on. Okay. So actually this configuration 1, I'm going to go ahead and hide this mesh. Okay. Might not be necessarily the best one. So I actually, if I go and jump through, I don't want to go into too much details about the different things and the different details of setting up study. But if I activate this configuration, this is third configuration, turns out to be the best one. And I actually have a plot here of the S parameters where we actually compare these, the 3 configurations. So configuration 3 is in blue. Maybe I can go ahead and make this a little bit thicker so that it's more visible for everyone. Because it's clear for me, but not necessarily for everyone. So we can go back to configuration 3, is the blue one. So because we wanted this to be work well around the 6.6 gigahertz, 6.7 gigahertz band, we see that the S parameters from these 3 configurations vary quite a bit. And actually, when we pick the configuration 3, we do get the matching that we need. We have better than 25 dB match at 6.7 gigahertz, and that was our frequency of interest. So at this point, I have a design that I think is working and is okay. It's centered at my desired frequency. So the next step is actually the subject matter of today's webinar is how do we actually go ahead and predict the power handling capabilities? Okay, and for this I'm going to go now into a little bit more of a detail in the subsequent studies. So I actually, to do this, we took this configuration 3 and we created 2 simulations. Okay, so this simulation 1, again, you notice the same kind of structure. We have the same material, same boundary conditions, and the same mesh, except that when we look at the port definition now, we see that here we said, okay, let's put 7,000 or 7 kilowatt. We expect this, and see, okay, if the breakdown is going to occur at this level. Okay, so that is really the way we do this. So we wanted to assess the peak power handling capabilities, and so in this case, so this is actually my my port excitation. But if I go back briefly to the air part, which is this cavity. Okay, by the way, you can always well, we can just maybe just do like this and isolate this part here. So this is the air part. Okay. If I look at the edit material, if I look at material properties, now this is air, and you'll notice that we have a property here, the material properties folder. Every material, every dielectric, every insulator that you work with, you will need to know its dielectric strength. So what is the dielectric strength of a material? It is the maximum electric field that material will support before the material becomes conductive. Okay. In the case of air, if the electric field strength exceeds 3 million volts per meter, then there will be arcing. In other words, the charges will move through air. Air is no longer insulator at that field strength. Okay. So then the question is, if I put 7,000 watts or 7 kilowatts in the structure, will this generate an arcing? Will the electric field generated exceed the maximum electric field, or will it exceed the breakdown value? Will it exceed the 3 million volts per meter? Again, if you're working with another material, some other insulator, maybe some ceramic or whatever, then you will obviously have a different level of dielectric strength. So that is really the main idea. The software is going to compute the fields everywhere in the structure, and now we want to see if it actually exceeded the dielectric strength. Now to do this, okay, I'm going to show you how this is done, but let me just elaborate a little bit more on this. Imagine for a moment that you have multiple materials. Let's say you have some different insulators with air and so on. Each material will have its dielectric strength. How do we know if there will be a breakdown or not? All right. So now we added this feature, which is the power feature, power handling feature, adds a safety factor plot. What is a safety factor plot? Essentially, safety factor plot, and you can see in this case, it's a folder where you can plot safety factor results. And you can see here that it's telling me that breakdown has occurred. It already knows that. So what is a safety factor? A safety factor is essentially a ratio of the electric field in each material, in each element of the mesh. It's the ratio between the actual electric field to the dielectric breakdown field. Okay, so if we're comparing what we have as a field compared to what the maximum the insulator can handle, then anytime we are below 1, we are safe. Okay, it means the electric field we have is actually less than the dielectric strength of the material, so there will be no breakdown. So arcing is not happening. Anytime the ratio exceeds 1, then we have arcing. So in this case, the software already computed this factor in the computational domain. It's actually telling me that there is breakdown. Breakdown has occurred. Okay. So now the question is, where did that breakdown occur? Okay. So I have already went ahead and generated a couple of plots. Okay. So now you see that my safety factor, this is the scale of my safety factor. So it should be between 0. Okay. Anytime it exceeds 1, then I had a breakdown. So you can see that my maximum field intensity here, I have a field that's going to exceed, 3 million volts per meter in this case, or a safety factor larger than 1. I can see it there. Okay, so through a section plot, I can plot this into an isosurface. So you can see this now. By the way, so an isosurface, I can maybe just go ahead and create, maybe show you how this is done. If I do an iso clipping, okay. So if I wanted to plot an isosurface, and I plotted the isosurfaces only, but of a certain value. So this is a safety factor of 0.5. Where am I at 50% of this length? If I want to go lower, where am I at, 18% of the, 0.18. So this is the surface, in the model where the safety factor, all the points that have the same value. So these are all the points that are at 0.14. Okay, I can see here, and maybe add to this the model edges to show. So you see where it is in the model that I have that level of safety factor. So this one, I would probably call this one a safety factor of maybe put this type 0.40. Okay, at 6.37 gigahertz at my central frequency, my matched frequency. Okay, so if I do that plot, I can have an additional plot. This one is a safety factor. I look at where does it exactly hit 1, and you can see in this case that it's hitting 1 very close to the tip, which is normal. That's what we expect. Okay. So this is really, we're at the borderline. This is where the breakdown starts to occur. If you were to go and put more than 7 kilowatts at the port, then this safety factor is going to exceed 1 more and more. So you see now, these are the elements. This is the area where the dielectric breakdown is going to occur. All right. So obviously, you can generate these plots in different formats and look at them and so on. You can also correlate this with the electric field distribution. So you can see, look at your electric field, obviously, so it's going to be similar, and you know that that's where your electric field is going to have the maximum field. And you can also, you can do other things. You can look at, how the wave propagates into this, and so you can do animations and things. But the focus again today is on the power handling. So this study, I hope I've shown you how do you figure out if you have breakdown or not, and what's your peak power handling capability. Okay, so that is one aspect. Okay. The next study is a study where we actually now look at the average power handling. So in this case, what we've done is we involved thermal. So when you see this icon of the simulation, it says we've done an S parameter simulation, computing S parameters, and we have the thermometer symbol. It means that we have coupled this to thermal. Okay, so if I go here, I can illustrate this to you. So you see here, this is my simulation setup. I'm calling this is what it's called, and this is the frequency at which I'm doing this simulation. I'm doing 2 points. and I have here the coupling analysis, and my thermal coupling is checked. Okay, so what I'm going to do now is essentially I want this the software to tell me for these frequencies, okay, how much temperature, what's the temperature going to be in my structure when I put 400 watts of power in. Okay, so a couple of things then to consider. Now, if you look at this study, there are a couple of noticeable differences. Number one, we have thermal inputs, which we didn't have before because we didn't have the thermal coupling. Number two, we have thermal results. Obviously, we have, that's our interest. We want to see what happens to the structure. And again, to go back to my structure, if I look at my copper material, for example, notice that when we edit the material property, we have this thermal conductivity. So if you need to do thermal coupling, make sure that your materials are have those thermal conductivity, okay, in there, because that is needed to be able to do thermal coupling. So let me also take this opportunity to go back and show you in applying materials, the HFWorks material library comes preloaded with lots of materials. So you don't need to worry about what's the conductivity of brass, for example, okay, or of bronze or some of these materials like silver. All these properties are predefined for you. Okay, it's only when you create or edit your own material that you need to, you need to have that information about the thermal properties of the material. Okay, so these are, we have metals, we have substrates, we have ceramics, we have LTCC and so on, cable materials and so on. So this is the standard library, quite extensive material library with these, like if we look, for example, at some of the substrate materials or some of the ceramic materials, then you see that the dielectric strength is predefined in there for you. So in this case, for example, for plexiglass, it's higher than air, okay, and the thermal conductivity is there as well. Okay, so it's the material library of HFWorks is actually a pretty good library for user to work with. So that's one. Number two, in the material, in the properties of the ports, in the boundary conditions of the ports, what we've done, we went ahead and said, okay, let's do the calculations, let's do the thermal coupling with 400 watts of power injected. Okay, so that is another part of the stuff. And then obviously, how is this thing cooled? Well, the package considers we can do, in terms of thermal inputs, we can do convection, we can do radiation. We do not do forced cooling. Okay, so we cannot say, okay, there is a forced cooling, because that would be a fluid dynamic problem. But all other aspects of thermal analysis are defined through this interface, and in this case, we're saying this is convection cooling, just natural convection of heat radiating out from the structure. So for the rest of the study, the properties are the same, the mesh is the same, and so on. Again, your electric field results and magnetic field results are not going to change much. You know, that's what we had before. And now the interesting part is to see, okay, how is the temperature distribution in this case. Okay, so obviously the temperature distribution is going to be mainly in the. So this is a plot, a section plot of the temperature distribution. We can plot the heat flux. We can put the temperature gradient. In this case, obviously, you want to make sure that your model does not exceed a certain temperature. If your limit is, let's say, 150 degrees or so, then you look in this case and say, okay, what is my maximum temperature? And maximum temperature is 131 degrees, okay, for 400 watts of power. And it's mainly being dissipated inside this the central conductor, because this central conductor doesn't have a lot of access to radiate power out, whereas the outer wall of the transition is more around 50 some degrees, in the 50-degree range, because it's it's convecting out, and it's being kept at slightly lower temperature, obviously, than the central conductor. So the temperature, obviously, you can do like you can do a ISO if you can make this into clipping, into ISO clipping, so you can look at where is the temperature the same, and you can do an inside-out plot. So this is a in Kelvin, this is a 355 Kelvin. Okay, so I can put you can play with this obviously at will. You can set the value. You can even have multiple ISO sections with different values, so you can layer them, and you can see that you have different concentric surfaces of temperature distributions. So you can generate a wide variety of temperature results. So in this case, the criterion obviously for power handling depends on what temperature, what's the maximum temperature that is considered, or that's acceptable for the design. This is in this case, for if we were to go back to the boundary conditions and we say, okay, now my port, I wanted to increase this power, okay, to 500 watt. Let me show you how that can be done very easily. So if you want to keep your original result, you just drag this and drop it on the main tree, and you can call this a 500 watt or 450 or whatever. Okay. So everything gets inherited, your material definitions are intact, your boundary conditions and so on. So all you'd have to do is essentially come here and say, edit this definition, and instead of 400, make this into a 500 watt input power, and then you get, the results obviously get invalidated. They're not consistent with the port definition, and then you'd be able to run this again, okay, and get the results and see what is the temperature like at that power level. So a combination of the dielectric strength properties of materials and the thermal solver that's now embedded in HFWorks are the tools that we are putting at your disposal to make power handling assessment and calculations. Okay, so I think I gave you a quick overview of how this feature works. Before I close, I'll probably just show you one additional feature. Obviously, if you spend time creating plots and setting all this up, the report generating feature is interesting. So this is where you document the work that you do. This is your table of content. Anything you want to include, you can check it. And anything that you don't need, if you don't want to need an appendix and maybe in the conclusion and so on, you don't have. So if you want to include some model views, for example, if you wanted to say, I wanted the top view without mesh, you can add that in there. As many views as you want of your model, the properties of your materials, the frequency setup, and all of that. Anything you want to include. And then you have the choice. This is where the file is going to be placed, and it's going to be a Word file, and you can show this inside SOLIDWORKS. So let's see how this works. So actually, you don't have to do any kind of screen captures and cut and paste and all of that stuff. That's all automatically done for you. And as it is done, it's brought into SOLIDWORKS. So this is the Word report. So this is our model. This is SOLIDWORKS. These are the results of HFWorks. This is the report inside SOLIDWORKS. And then, of course, once you are inside SolidWorks, if you want to edit anything, and you write, introduction and whatever stuff you need, the full formatting power of Word is there for you. You can highlight text and underline and so on. You can jump right off to, let's say, the safety factor plot, for example. You want to see that. So that's my safety factor plot. So you see in this case we are 0.26, at 400 watts. So we don't reach the breakdown. Obviously, other plots that you generated would be there. This magnetic field, electric field plots. Anything you create gets automatically captured into the reports in this report. And so in this case we have some S parameter plots in Smith chart and so on. Any of these pictures so this is my temperature result. All of these pictures, obviously, you can move them around a little bit. You can, crop or do whatever you need to do to them. So really, it's a very powerful feature that we put at your disposal, because your report is here, and you're in always the same work environment inside of SolidWorks. So I think this gives you all a brief idea. I'd like probably to see if there are some questions that we can answer.
Yes, Dr. Cookie, thank you for your presentation. And now the floor is open for questions. So if you guys can type your questions in the chat box, and Dr. Cookie will answer them as they come.
So question is there a limit to the number of ports you can have? No, there is actually no limit to the number of ports. The idea also for thermal purposes, and even for the safety factor purposes, if you excite multiple ports simultaneously, then the power obviously inside your structure is going to add up. The losses that they're going to generate are going to add up as well, and consequently the thermal and the heating and so on is going to add up. So the software is able to handle multiple ports without restrictions, and you can use a combination of port excitations to do your assessment from a breakdown standpoint or from a thermal handling or thermal heating standpoint. So I hope that answers the question. Okay, so another question is is about any other examples or structures. Let me just point you to this thing. In HFWorks we have a neat thing called the demo viewer. Okay, so the software actually ships with a whole number of different examples. They're all organized through a demo viewer. So the demo viewer is not just SolidWorks models. Demo viewer is actually models that are ready to be solved, and if you solve them, they become tagged as solved. So in this case, I have the basic models. So I have antenna models. Okay, I have them actually. They're planar antenna models. I have waveguide antenna models. I have a one wire antenna model. I have cavity resonance models. Okay, so cavity resonators or printed resonators. And I have a whole bunch of S parameter models that are ready to be simulated. I have some connectors and transitions. Like in this case, you have multiple ports. I have different filters. And I have, we have even for beginners very simple examples. How do you actually get a two-port simulation and look at the field plots and so on? So the demo viewer is a place where you can find some additional examples on HFWorks capabilities. So for example, to go back to the question about multiple ports, so in this case, if I look at this, if I open this file, this is a die assembly. Somebody is making a PCB and it makes a chip and they want to see what happens if the chip heats up and so on. So this is a typical example where you can have different ports. Some of them have differential excitation or single-ended excitations and so on. And it's really no restrictions as long as you are able to draw the model inside SolidWorks. So okay, how do all right, so the boundary condition, the thermal boundary condition outside of the so that's the question, I think. Let me read that again. How to do a thermal boundary outside the adapter here outside. Okay. Actually, this model is quite. Yes. So the way to do it is essentially to select. Hang on a second here because I need to set this up. Okay. So let me go back. So actually, this one has. So I'll get back again to the question about the thermal boundary condition. So this one has all in all has 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ports in this simulation. Okay. But we're not going to do this one. So let me go back to my model. So the question is, how do we set up the thermal input? So if you look at in this case, okay, what we've done, and if I edit this definition, we've said that essentially these faces have a convection boundary condition, okay, on them. So essentially, it's convection cooling, okay, that we're saying. And it's applied to all outer surfaces. Okay, so that's how we do it. So in general, the process of let me say, for example, the process of applying either thermal or electric boundary conditions. How do we do it? So the process is really very simple. So if I wanted, let's say, if I go here and I want to say, okay, I have a symmetry boundary condition, to take a different example. If I wanted to have a perfect magnetic symmetry boundary condition, you select it, and then you select the entities. So the, PMC can be applied only to surfaces. So you go, and any surface to which you want to apply the boundary condition, you just click on it, and it gets added to this. This is standard SolidWorks operation. Okay. If you pick to do something else, let's say if I wanted to do a perfect electroconductor, okay, then this boundary condition can apply either to a face or to a body. So if I have this whole thing that's made out of, okay, if this whole outer body is, I wanted it to be considered as PEC, not as copper, I can do that. I can select it and say apply PEC to a body. Or if I wanted to, I can clear the selection. If I want to say, oh, it's actually, I want certain surfaces, this face, for example. And sometimes you might want to see, okay, show me the face. Which face am I talking about, right? So you have this symbol that you can show preview, and you can make it bigger or smaller. And then you can see that that's the face that we're talking about. So, so we have a lot, obviously, of features inside the software that allow you to define these kinds of boundary condition. The same thing for thermal inputs. If I want to say I have a radiation boundary condition, a thermal radiation, then it only applies to surfaces. Then I can select these outer surfaces with simple clicking and say, okay, all of these surfaces are going to have radiation boundary conditions. Okay, and that will obviously do it. So if I created that, it gets added to the list of boundary conditions, and obviously my thermal results get invalidated because of that. All right, so I hope that answers that question about the thermal. Okay.
Okay, are there any more questions, Dr. Cookie?
I'm going through the list. I think I've pretty much addressed all of them.
I think the gentleman is asking you, radiation boundary condition, is it okay? Do you see that? Same gentleman that asked about the temperature and how to set up the boundary conditions for the...
Yeah. So I think the radiation boundary condition is obviously, I mean, if you don't have, you can choose that. You can use the radiation boundary condition. The user is obviously have to know the specifics of their situation, of their physical situation. So if you have a, for example, for space applications or whatever, and you have a radiation boundary condition, thermal radiation boundary condition, then yeah, obviously that's something that can be used, and it's okay.
So do you see any more questions there? I don't see any more.
I think those were the key ones. Maybe okay. So okay, there was one more. So this is the question about coupling to flow simulation, like exporting some of our electromagnetic results into other SolidWorks. I think we encourage all SolidWorks users to ask SolidWorks to make this possible. We've been open. We wanted to do this, and we've been trying to do this with SolidWorks. It's just that SolidWorks simulation folks have not made this this easy with APIs and things. So we still hold hope that they're going to make it easy for us. We do provide some features in terms of export capabilities of results. So if you have a result, you can go and generate a listing of data, and so you'd have the nodes, the field value, and the XYZ, in this case in inches. You can export that, and then what you do with that is obviously, so in this case we're exporting the electric field. In other case we can export any of the results that we put out there. So the rest of it, how to import it and what to do with it, is a challenge, particularly because the mesh is not the same. But so there has to be some interpolation. If we give you different XYZ coordinates of our mesh from the SolidWorks mesh, then something has to be done there. It would be easier if we had more APIs and an automated process, and I think when users put pressure on SolidWorks, then I think there could be some movement there.
Let's hope that happens, and they contact SolidWorks for that. If there is no more questions, we're going to end this webinar, and so we'll just double check here, wait a minute or two before we end it. Any case, I wanted to thank everybody for attending and spending the time and looking and checking our software HFWorks. I will be sending you a recording of this webinar come Thursday or Friday. We're also going to post it on our website at www.emworks.com. and we'll also talk to you probably, I mean, after the webinar, or invite you some more webinars as we go. I guess with this picture of what you see on the screen, this animation, I'd like to thank you all, and this webinar is now over, and you all take care now. Bye bye.